fangen wir an. Heute ist der 20. Der 7. April 2020. Vorlesung Projektmanagement und wir fangen an mit der we start with the formalization. When I say formalization, we speak in mathematical terms. Of complex network dynamics. Okay. What we have called Yokotenkai. This is a Japanese word which can be written like this. Let me see if I can remember. Basically, this, something like this. Yoko. But of course, this is not important for the exam, just so that you have seen it. Yokotenkai. Okay. This means the spreading dynamics that's known as Yokotenkai, also meaning standardization or horizontal standardization of behavioral patterns among organizational clusters. Spreading phenomena are ubiquitous in nature and society and have been extensively modeled in network theory to explain outbreaks of infectious diseases or the diffusion of innovations. You are probably aware of this spread worldwide of the virus corona. This is going to be explained through the mathematical terms that we are going to see today. Okay. This lecture today aims to explain how these spreading phenomena behave dynamically. Okay, so we are going to see how spreading phenomena behavior takes place and how it dynamically behaves. And therefore, if we can explain it, we can compare how organizational design configuration affect standardization. Okay, and this is our goal. We want to see how the organizational dynamics affect organizational design and vice versa. To model the process, we start by making two assumptions. Two assumptions that aim to make the mathematical model easier to explain without losing much plausibility. First assumption is we need to assume that individuals can be in two different states. Individuals are or can be in two different states. S, susceptible individuals that have not yet been contacted by the behavioral pattern or by the virus, or I, infectious individuals that know the behavioral pattern and can therefore infect others with it. Okay, so those that have been infected already. And so this is the first assumption. We have two types of individuals. First assumption. And second assumption. The second assumption is that we need to assume that each individual can infect anyone else. Each individual can infect anyone else. So I repeat, we make two assumptions. Okay. And the first assumption is that individuals can be in two different states, susceptible. Those are individuals that have not yet been contacted by the behavioral pattern or by the virus, and infectious, individuals that know the behavioral pattern and can therefore infect others with it. Second assumption, we need to assume that each individual can infect anyone else. This assumption is called homogeneous mixing hypothesis. We will relax and we will see later on why this hypothesis is not real, but we need to start by doing this. So, any questions, please? Any questions? By taking these two assumptions, if there are no questions, by taking these two assumptions, we can make a first approximation of the standardization process, Yoko Tenkai, standardization dynamics, and the process can be considered analogous to the so-called susceptible infectious susceptible. In short, SIS model, in which we consider a behavioral pattern like a disease, like a virus that spreads in a population and allow for individuals to forget the behavioral pattern and abandon it. So this is our first approximation. It's called susceptible infectious susceptible, okay, in which we consider a behavioral pattern that spreads like a disease. So we teach something to the population in the organization. We teach some pattern like the cpDNA, for instance, or lean management, something like that. And we have two hypotheses or two assumptions. First, that we have two types of individuals, susceptible and infectious. And we assume the homogeneous mixing hypothesis. So anybody can infect anybody else. This is not going to be true later on. We will see, because I am going to copy, for instance, when I am in organizations, I am going to copy the behavior of my boss, not the behavior of my people. So there are things that are going to be different in reality, but we take a first approach like with this model. So because, we continue in the second page, because of the homogeneous mixing hypothesis, HMH, the number of infected individuals given by I as a function of time changes with time at a rate given by, so the speed of infection, if you want, the speed of infection of the virus or the behavioral pattern given by this equation. This is the speed, and I will explain in a minute what this all means. Beta, first momentum of K times I times 1 minus I minus mu. This is the equation. Danke, Tim. Jetzt sollte jetzt drin sein. Irgendein Grund. So, this is jetzt drin. So this is the equation, and what this all means. Well, let me do it term by term. I of t represents the fraction of individuals who have been infected by the pattern beta is the rate of infection. K, first momentum of K is the average network degree. We already know this from our network knowledge, and mu multiplied by E is the forgetfulness rate at which the population unlearn the pattern. If we think about it as a virus, this would be mu multiplied by E would be the curation rate, okay? How fast do I get cured by the virus? E represents the fraction of individuals that are infected by the virus or by the behavioral pattern. Beta is the rate of infection. K is the average network degree, and mu multiplied by E is the forgetfulness rate. Okay. So the solution to the equation, this is a differential equation of first degree. The solution of this equation is quite easy. If we take I0, meaning I at the time equals 0, the solution of this equation is I of t equals 1 minus mu divided by beta k times c e beta k minus mu multiplied by t divided by 1 plus c e beta k minus mu multiplied by t, where c equals I0 divided by 1 minus I0 minus mu divided by beta. Okay, so this is the solution. If we take time to infinite, and we say that the infection rate at the limit, when time goes to infinite, equals 1 minus 1 divided by R0, where R0 is a very important concept that you should know by now. Is R0 is the reproductive number, and is beta divided by no, beta times k divided by mu. Okay. As can be easily deducted, if R0 is bigger than 1, then the behavioral pattern standard is poised to spread and persist in the organization. So if R0 of the coronavirus is bigger than 1, then we will never get rid of it. Okay, so the behavioral pattern spreads and stays in the organization. If R0 is smaller than 1, then the virus dies. So the goal of all the people taking care of coronavirus right now in the world is to get R0 below 1, because then the behavioral pattern, the virus, dies out. So I can only infect less than 1 person. I am infected, so I can only infect less than 1 person, and that's bad because the virus or the behavioral pattern doesn't get spread. So it can be said that the higher R0, the faster is the behavioral pattern spreading. Okay. But what is R0? Does it mean that R0 is bigger than 1? It means that Bk is bigger than mu. Okay, and this means that the infection is bigger than the forgetfulness. Okay, so infection is faster than curation. That's what it means. Okay. There's a question here. If we can make an example. I don't exactly know what you mean with an example, Kim. This is just theory. Okay. This is network dynamic theory, and I don't understand what you mean by example. What formula do you get? There's a question by what formula? Number 1. Could you again explain the formula? Yes. So this formula is telling us that the rate of infection, the rate is a speed, okay? The change of the infection with time is equals 1 beta, okay? One parameter given the speed of infection, one parameter describing the network structure, the network degree, the infected people, multiplied by the not infected people. One minus the infected people is the not infected people, and this is subtracted to the people that have already forgotten the behavioral pattern or are cured by the virus or don't have the virus anymore. Okay, I always make the analogy of the behavioral pattern and the virus. So we have the parameter describing the infection rate, and the forgetfulness rate. There are two, and they're fighting all the time. Okay, so we have one parameter trying to infect the people. This is the first parameter. If you want the rosa, and then we have the violet, those that are forgetting the behavioral pattern or that are getting cured. And this is represented by this formula. If we solve this equation, and this solution, I am not going to do it because it's something that you should already know, or maybe it's given in another math course. This is a first degree differential equation. It's not difficult. You get this, okay? And you get this solution given by equation 2, where the important message is given by this number 3. Okay, so this is the important message. Reproductive number is what you should be taking care of. R0. Because R0, you need to understand what R0 means. Because R0 is describing the success or failure of the organizational behavioral pattern infection. We want the organization to behave in a certain way. And if we get an R0 bigger than 1, then we are going to be successful. If we get an R0 smaller than 1, then we are not going to be successful. Okay. And this is basically what we want to understand. This you need to understand, and you need to explain. Okay. We make a little break. In 10 minutes, I send you another meeting invitation. The last parameter of the formula, mu multiplied by IT. So mu multiplied by IT is the forgetfulness. So people that get cured, that do forget the behavioral pattern that we're trying to teach them. So imagine in the last semester, you learned about statistics and now you forgot. So there are a certain amount of people in your population of 17 or 20 people in your course that have forgotten about statistics. This is given by this pattern or by this parameter. The amount of people that have forgotten about the behavioral pattern that was given to them. This is what it explains. Okay? No problem. So in 10 minutes, I send you another invitation to continue with this SIS model. We will see a second model that is closer to reality. See you in a minute. Bye. So our first approximation of Yoko Tenkai SIS did not incorporate the structure of the organizational network in which the behavioral pattern spreads. Okay, and in fact, the assumption that each individual can infect anyone else, this homogeneous mixing hypothesis, is false. Individuals can only transmit best practice or a behavioral pattern or a virus only to those they come in contact with. So this takes us to our second approximation. To network, so-called network epidemics. Because our new assumption is that individuals, individuals can only transmit the behavioral pattern or the virus to those they come in contact with. That's why one of the measures to keep coronavirus in check is to get the people at home, okay, so that they don't have contacts with each other. If social distance is practiced, then we can control the spread of the virus. For this, in order to explain this mathematically, we need to explain one concept that is that comes from statistics, and you probably know it already from statistics, is that the momentum of the degree distribution. The nth momentum of the degree distribution is defined as the sum of k p sub k. Okay. If n is 1, then we have the average degree. And this is one we already know. Okay. Okay, we can even calculate it with the equations from last semester. If n is 2, this is the second moment. It measures the spreads, measures the spread in the degree. Okay, if you want, in other words, it explains the degree heterogeneity. Okay. And one important issue that we will see in a minute is that scale-free networks, that's why we want them, networks have a second momentum that tends to infinitum. This means they're indistinguishable. You cannot distinguish them. When you look at them at any scale, you cannot say at which scale you are. So the continuum form of equation 1 with the assumptions that we have seen before, that individuals can transmit best practice or the behavioral pattern only to those they come in contact with, are or takes following form. Okay. This is equation number 5. Where phi sub k represents the fraction of infected neighbors of a susceptible node with degree k. So how many of my neighbors have been infected who have a degree k, a number of neighbors of k, and I small sub k equals I big sub k divided by n sub k is the fraction of nodes with degree k that are infected among all nodes with degree k. So now, if and the solution, it takes a little bit to solve that equation, but and of course I'm not going to ask you to solve the equation. If we take only the first order terms of the differential equation, we get the condition for global spread of the behavioral trait, behavioral pattern is given when the so-called characteristic time to reach 1 divided by E fraction of the system, of the population, tau is positive or have been infected. So tau tells me the amount of time it takes to infect 1 divided by the number E, 2.7 something, of the population. And tau is equals the first momentum of the degree distribution divided by beta times the second momentum minus the first momentum times the forgetfulness rate. Equation number 6. The result eine Zusammenfassung auf Deutsch. Ja, ich kann es nachher nochmal wiederholen, aber erstmal will ich fertig werden. To predict when an organizational design configuration will spread as a certain behavioral pattern. So in order to predict if or when a behavioral pattern will spread on a certain organizational design, okay, following condition needs to be fulfilled. This is given that it takes that lambda equals beta divided by mu, so the infection rate divided by the curation rate or forgetfulness rate needs to be bigger than the first momentum divided by the second momentum. And this is lambda sub c. And this is important because beta and mu are a function of the virus or behavioral pattern. But K and K square are a function of the organizational design. With the example of coronavirus, if the infection rate is very high and the curation rate is very slow, then it takes a very big lambda, okay? So it is very likely that the virus will spread because this condition is very likely to succeed. So what do we need to do as a society? We need to make sure that K divided by K squared is even bigger. And this can only be made with social distancing. Okay, this is so important. This is the reason why it's so important to make sure that you stay at home. We called lambda sub C the epidemic threshold. Okay, for the Yoko-Tenkai process. And this epidemic threshold is the threshold to successfully spread best practice behavioral traits within organizations. So, management implications. The first important aspect for the lean practitioner to notice is that the characteristic time depends on both the nature of the best practice to be transmitted and the network's topology. But the epidemic threshold, lambda sub C, depends solely on the organizational design topology. Okay, this is what I have already told. In fact, by measuring K and K squared for any given topology, we can determine this threshold at any given point in time. So it is advisable to know the organizational behavior or to know the organizational design to measure this in order to know a priori if our behavioral trait is going to succeed or not. High lambda means that organizational culture transmit best practice behavioral traits rapidly. High lambda means that the organizational culture transmits best practice behavioral traits rapidly. High beta and or that best practice is not easily abandoned, low mu once installed. Okay, I repeat, management implications. You have already one here, okay? That beta and mu are a function of the behavioral pattern, and K squared are just a function of the organizational design. The second one is that high lambda means that the organizational culture transmits best practice rapidly. So this means high beta. And or that best practice is not easily abandoned. Low mu once installed. So low lambda means exactly the opposite. Okay, and either you get best practice very slowly in place, or that you easily abandon it. Scale-free networks have a K square almost infinite, which means that lambda sub C is almost zero, which means that if you have a scale-free network and you install lean management or any other behavioral trait, then you get success almost for sure. Okay, that's why if you have a scale-free network like the internet, and that's why I wanted you to look at different networks last week, viruses spread very fast. That's why people or the authorities are asking people to stay at home because of coronavirus in order to get lambda sub C very high so that the virus doesn't spread. Okay? So, any questions? Ja, dann mache ich eine schnelle Zusammenfassung auf Deutsch. Die zweite Approximation auf dem Konzept ist, dass Menschen können nur diese Verhaltensmuster an anderen Menschen weitergeben. Ja, Flo, lass mich bitte eine Frage beantworten und dann kommen wir zum nächsten, okay? Menschen können nur Verhaltensmuster weitergeben an anderen, indem sie oder mit denen sie in Kontakt kommen, okay? Und das heißt, das ändert unsere erste Annäherung. Dafür, um das zu erklären, benötigen wir diese Momente der Statistik. Okay? Und das ist wichtig, weil das erste Momentum ist das Average Degree, das kennen wir schon. Das zweite Momentum misst den Spread, die Geschwindigkeit, in dem diese Degrees sich verteilen. Okay? Wie homogen sie sind in dem Netzwerk. Scale-Free Networks haben eine Eigenschaft, und zwar das zweite Momentum ist unendlich oder fast unendlich. Die Formel Nummer 5 beschreibt das Verhalten in einem Continuum. Okay? Und das grundsätzlich konzeptuell ist das Gleiche. Das erste Term beschreibt die Infektion. Das zweite beschreibt die Forgetfulness oder die Duration. Ja, wie schnell ich wieder gesund werde oder wie schnell vergesse ich den Verhaltensmuster. So, die Lösung dafür, für diese differenzielle Gleichung, ist, dass die Zeit, die es notwendig ist, um 1 geteilt durch E der gesamten Population zu infizieren, Tau, ist gegeben durch diesen Ausdruck Nummer 6, erste Momentum geteilt durch Beta mal K zweite Momentum minus K erste Momentum mal μ. Und damit Tau positiv ist, heißt es, dass das hier unten muss größer 0 sein. Okay, versteht sich? Ansonsten habe ich ein Problem und dann kriege ich keine positive Zeit. Von daher kommen wir auf diesen Ausdruck von Lambda. Die Kondition, damit Tau überhaupt existiert, beziehungsweise größer 0 ist dass Lambda, also Beta geteilt durch μ, also die Ansteckungsrate geteilt durch die Genesungsrate, muss größer sein als K, also als das erste Momentum geteilt durch das zweite Momentum. Und das ist Lambda sub C. Das ist dieses Epidemic Threshold. Die erste Botschaft, die wichtig ist für uns, ist, dass Beta und μ sind eine Funktion von dem Virus oder von dem Behavioral Pattern. K und K Quadrat sind nur eine Funktion von dem Organisationsdesign. also von der Struktur von dem Netzwerk. Und das ist wichtig. Und das können wir kontrollieren. Wir können die Population zum Beispiel nach Hause schicken. Die zweite Botschaft und die dritte ist eigentlich das Gleiche, ist, dass hohe Werte von Lambda bedeuten, dass die Kultur entweder die Best Practice schnell weitergibt, also hohes Lambda, oder das sehr langsam vergisst. Kleines Mühe. Ja? Genau das gleiche wie ein geringfügiges Lambda. Und SFN, also Scale-Free Networks, haben ein zweites Momentum, der ist tendiert zu unendlich. Und das bedeutet, dass der Threshold fast null ist. Das bedeutet, dass unsere Verhaltensmuster, die wir installieren wollen in solchen Organisationen, fast immer erfolgreich installiert werden, wenn sie gut sind oder wenn sie schlecht sind. Die Frage von Flo, gehört das zu letzter Woche zu 5.1? Selbstverständlich, wir reden immer über Cyber-Physical Networks. Okay? Wir reden immer über die gleiche Systeme. Nichtsdestotrotz, ich habe versucht, in dieser Vorlesung euch einen Hinweis zu geben, ein mathematischer Hinweis, wie die Netzwerke sich dynamisch verhalten, weil das ist gerade so aktuell. Und ich habe euch versucht mitzuteilen, mathematisch, wie sich Netzwerke verhalten. Durch diese Formalisierung des Yokoten-Geis, damit ihr versteht, warum ihr daheim bleiben müsst. Das ist ganz wichtig, weil wenn wir nicht als Population unsere Organisationsstruktur ändern, nämlich durch diese Änderung von K und K hoch Quadrat, können wir nicht das Verteilen von dem Coronavirus dann meiden. Geht nicht. Okay? Gibt es weitere Fragen? Fragen? Gut, dann diese Inhalte werde ich jetzt hochladen auf prof.h4.com. Jetzt seid ihr in der Lage, seit heute auch euren Bekannten mitzuteilen, warum wir daheim bleiben müssen in diesen Coronavirus-Zeiten. Und das könnt ihr auch mittels Mathematik erklären. Ganz wichtig. Nicht nur für Projektmanagement, aber auch für das allgemeine Leben. Diese Gleichungen und diese Mathe ist ganz wichtig für die momentane Situation. Okay? Also gibt es bitte auf jeden Fall weiter. Kim fragt, ob es klausurrelevant ist. Das ist süß, Kim. Selbstverständlich ist es klausurrelevant. Radoslav, nein, es gibt später keine Vorlesungen mehr. Ich mache heute nur den ersten Block. Alles, was wir hier sehen, ist klausurrelevant. Ich weiß nicht, warum überhaupt die Fragen kommen. Noch Fragen? Gut, dann lade ich das Ganze hoch wieder und ich bitte euch, diese Inhalte weiterzugeben an Menschen, die Interesse haben, zu verstehen, wie und warum das Coronavirus so wichtig ist und wie wir das bremsen können. Bis dann. Servus.